Hello students, in the last session we studied about induction approach, deductive approach, mathematical statements and a few examples from mathematical statements. Today we shall study about principle of mathematical induction. Suppose there is a given statement P of n involving the natural number n such that the statement is true for n is equal to 1, that is P of 1 is true, and if the statement is true for n is equal to k plus 1, that is truth of p k implies the truth of p k plus 1, then P of n is true for all natural numbers n. Here property 1 is simply a statement of fact. There may be a situation when a statement is true for all n greater than or equal to 4. In this case, step 1 will start from n is equal to 4 and we shall verify the result for n is equal to 4, that is P of 4, whereas property 2 is a conditional property. It does not assert that the given statement is true for n is equal to k, but only that if it is true for n is equal to k, then it is also true for n is equal to k plus 1. So, to prove that the property holds, only prove that conditional proposition. What is that conditional proposition? If the statement is true for n is equal to k, then it is also true for n is equal to k plus 1. This is sometimes referred to as inductive step. The assumption that the given statement is true for n is equal to k, then it is also true for n is equal to k plus 1. The assumption that the given statement is true for n is equal to k in the inductive step is also called the inductive hypothesis. To prove that a statement P of n is true for all natural numbers n, we have to go through two steps for principle of mathematical induction. Let us see what are they. First is to verify the result for n is equal to 1. Second, assume the result is true for n is equal to k and then prove the result for n is equal to k plus 1. Here we have a special remark to make. We emphasize that the proof by mathematical induction requires the fulfillment of both the conditions first and second as stated above. Now, after learning the principle of mathematical induction, students, let us see how we can solve the mathematical statement like sum of first n odd natural numbers is n square. First, let P n be the statement 1 plus 3 plus 5 plus to n terms is equal to n square, which again can be rewritten as 1 plus 3 plus 5 plus 2 n minus 1 is equal to n square. Did you observe how we obtain 2 n minus 1 here? Look, the given numbers are forming an AP 1, 3 and 5. First term is 1 and common difference is 2. So, the nth term can be written as 1 plus n minus 1 into 2, which is simplified as 2 n minus 1. Now, step 1, P 1 means 1 is equal to 1 square, which is true. That implies P of 1 is true. In step 2, P m is true, that is 1 plus 3 plus 5 plus 2 m minus 1 is equal to m square. Take this equation as 1. Now, we shall prove that P of m plus 1 is true. For that, 1 plus 3 plus 5 plus 2 m plus 1 minus 1 is equal to m plus 1 whole square. is to be proved. 1 plus 3 plus 5 plus 2m plus 1 terms, that can be rewritten as 1 plus 3 plus 5 plus 2m minus 1 plus 2m plus 1. Using the first equation, we can rewrite this as m square plus 2m plus 1. This is an expansion of a binomial and we could write it as m plus 1 whole square. That implies p of m plus 1 is true. Hence, by the principle of mathematical induction, p of n is true for all n. Therefore, the sum of first n odd natural numbers is n square. Now, let us solve one more question using principle of mathematical induction for all natural numbers. 1 square plus 2 square plus 3 square plus n square is equal to 1 upon 6 n into n plus 1 into 2n plus 1. Let p n be the statement given by p of n 1 square plus 2 square plus 3 square plus n square is equal to 1/6 n into n plus 1 2n plus 1. In step 1, p of 1 is equal to 1 square, which is equal to 1 upon 6 into 1, 1 plus 1 into 2 into 1 plus 1, which can be simplified as 1 upon 6 into 2 into 3. This gives us 1 is equal to 1. Therefore, p of 1 is true. In the second step, let p of m be true, then 1 square plus 2 square plus 3 square plus m square plus m plus 1 whole square is equal to 1 upon 6 m plus 1 plus 1 into 2 into m plus 1 plus 1. Now, 1 upon 6 m into m plus 1 to m plus 1 plus m plus 1 whole square, because from first equation we can rewrite it as 1 upon 6 m into m plus 1 into 2m plus 1 plus m plus 1 whole square. Taking 1 upon 6 m plus 1 outside the brackets, we can simplify it as m into 2m plus 1 plus 6 into m plus 1. This again can be written as 1 upon 6 m plus 1 2m square plus m plus 6m plus 6. On simplification, we get 1 upon 6 m plus 1 into 2m square plus 7m plus 6. See, we have got a quadratic polynomial here, which can be factorized using splitting of middle term. 1 upon 6 m plus 1 into 2m square plus 4m plus 3m plus 6. That can be written as 1 upon 6 m plus 1, 2m into m plus 2 plus 3 into m plus 2, which can be factorized as 1 upon 6 into m plus 1, m plus 2, 2m plus 3, which again can be shown as 1 upon 6 m plus 1, m plus 1 plus 1, 2 into m plus 1 plus 1. That implies p of m plus 1 is true. Hence, by the principle of mathematical induction, p of n is true for all the natural numbers n belonging to n. So, let us summarize today what we have studied. The principle of mathematical induction is one such tool which can be used to prove a wide variety of mathematical statements. Each such statement is assumed as p of n associated with positive integer n, for which the correctness for the case n is equal to 1 is examined. Then, assuming the truth of p of k for some positive integer k, the truth of p of k plus 1 is established. Today, we have solved some questions based on this, and the rest of the questions we shall continue in the next session.